All right, everyone. So what is high performance computing? High performance computing is the ability of a computing system, a set of servers, to perform massively parallel operations with maximum throughput, minimum latency, and predictable orchestration across the nodes, across the servers. So why does it matter now? It's super important because it's the practice that enables companies to train AI models, to inference the AI models that you use every day to learn new things and create and design images and create virtual worlds and use coding tools to create new programs and accelerate your business and improve your life. And also, companies are going out there and they're simulating the behavior of airplane components, and they're finding new medicines by simulating the human body and particle work and particles, and the finance industry is using it to simulate different outcomes, and armies of agents are being built out to use tools dynamically and do all sorts of things like automatically discover new materials that can improve quality of life and reduce the impact on the planet. And so it allows companies to iterate on designs 10 times faster by using simulation. It reduces the danger of creating dangerous scenarios. For example, with nuclear energy, or simulating a hurricane going to a building and being able to design better buildings based on that, or simulating a poison in a body. It can save a lot of time and a lot of money to test all kinds of scenarios and make products safer. And then also, if you come out with optimized, better products because you simulated more possibilities, you're going to have better products. So high performance computing is key to this process, and even it's going to enable personalized medicine and all kinds of things. Even the algorithm, your Whoop algorithm, that's high performance computing for thousands of people. And so, all right, so what's happening at the physical layer? Well, there's tons of servers. There's a data center, rows and rows of servers. There's the power, the energy that goes into enabling that. There's the cooling that keeps the temperature good and it doesn't mess with the data, because the data can get messed with. And then there's all the cabling and the distribution to the entire world. So that's the physical layer. What's at the hardware layer? At the hardware layer, we have 5 main components that I'm going to talk about right now. But we have the node, which is like the server. And then the server is composed of CPUs, GPUs, memory, and the network linking. And so let's start with GPU. So GPU, everybody talks about GPU. Okay, so it's what is used to train and inference large language models. What it is a structure with thousands of parallel cores that specialize on doing a very specific set of tasks, usually linear algebra and matrix-heavy workloads. And they also are great for graphics processing, for changing a bunch of graphics in real time for your videos. And they're becoming increasingly good at LLM work. And there's variations of similar chips, which are TPUs, tensor processing units, and LPUs, which are very specialized on language processing. And they enable us to simulate climate conditions by having thousands of molecules change in real time, or in a biological setting in a body, simulating thousands of biological changes in real time. It's all parallel. And all right, then we have CPUs. CPUs tell a computer how to act. They're the brain of the computer, and they direct the decision flows. They handle the logic, the control flow, and the data movement. And they handle, in HPC, in high performance computing, they handle job coordination, so managing and distributing the different workloads, preparing data before the GPU goes on it, and then aggregating the results after and storing it and distributing it, and serial computations. So the way they're structured is, GPUs are these parallel thousands of cores. Here it's a limited, small handful set of cores that do sequential processing, so one at a time. GPUs all at the same time, CPU is one at a time, and they work together. CPUs orchestrate, GPUs accelerate. And I think it's important to note that the hardware is very key. And if we start to think about the other components, it's memory manages data. And so we have very fast access memory, which are the registers and the cache, which handle the data inside of the GPU and the CPU that it's using in real time to do things like managing the different pixels that are changing in a video, or allowing you to see multiple scroll through on your phone screen and see like 3 posts at the same time. That's all in the cache. That's all loaded in there. And then we have the main memory, which allows you to access hot data. So it's a little bit slower because it's like a separate component, but it is still data that is currently being used in real time and is very relevant to the current tasks that you're doing. And then we have something more cold storage. Cold storage allows you to store things in the long term. Think about Instagram posts that you have archived that you only pull out in certain instances, or your pictures in Box, or that kind of thing that's cold, that's not being used in real time and served in real time. And then we have the network link. So the network links will link different GPUs together to operate in real time to do things like train AI models and inference AI models. And then we have the interconnect layer that's broader, and that will connect multiple nodes together to train models and share the information between the models so that they can have a shared memory of what's happening and they can train properly. So if we zoom out a little bit, CPUs manage orchestration, GPUs and accelerators execute the math and the parallel processing at scale. The memory and the cache feed the data at nanospeed seconds. The interconnects ensure the coherence across the GPUs and CPUs at the node layer, and then also at the between nodes, between server layer. And the storage will preserve the history of everything that's happened and the state, and allows us to store vast amounts of data. Then we have the software layer, and this is where, so on top of the hardware, we have the operating system, which joins the hardware, which connects it all. And often in high performance computing, it's a version of Linux. And here we have Red Hat OpenShift. We have Red Hat Enterprise Linux is an example of one, and it handles the communication between the software and the actual hardware components. It'll run directly on the bare metal servers. And so what happens is we have another layer on top of that, which is OpenShift, which will actually handle the management of different nodes to talk to each other and actually perform the operations of an app in a way that's elastic. So when the workload is high, think about Christmas, everybody's ordering things on Amazon, and that's where the workload is high. You need more nodes to be working together. OpenShift will allow you to scale up automatically. And then, things are lower, then you need just less nodes, less resources, and you're able to do that automatically. Another use case is the same for example, you're scheduling a training run to train a geospatial model to predict climate on the planet. OpenShift will automatically handle the rule setting and the decision making of how many nodes do I need for this training run, depending on the certain conditions. And it's pretty powerful. It's a control plane for multiple nodes. And on top of that, we have the applications, right? So the actual containers, the things that hold the AI apps that you love to use, hold, YouTube, hold the actual runtimes, the actual application containers. And these application containers are distributed across different nodes, across different operating systems, and OpenShift is dynamically scaling the use of the containers. And it's very critical. I mean, just keep in mind, I think just something important for you to keep in mind is, some of the developer frameworks that are used. So CUDA is used for GPU acceleration. So is ROCm from AMD for GPU acceleration. MPI, message passing interface, for inter-node communication. So how do you ensure nodes are communicating properly in a high-performance computing run? And then also OpenMP for multi-threaded CPU operations, and OpenCL for cross-platform compute acceleration, connecting different platforms. And then, so just keep in mind that everything is working together, again, to achieve different simulations, to achieve different flows, to achieve the operation of different applications, to achieve inference runs. And that's the art of high performance computing, the orchestration of massive amounts of servers to achieve a goal, like train a model, like make inferences, in autonomous cars where CPUs are handling the decision making and control flow while the GPUs process the actual vision, the camera, and the LiDAR in parallel. And then if you combine the two, you get real-time perception of the things that are happening and then decision loops from the CPU to occur within milliseconds. So it's all a combination. They all work together. In a video game, you walk into a fire and then the graphics change and like you get like a super cool effect. That's the GPU, but the actual trigger that made that fire occur was a CPU in operation. And that's all stored in the game data, in the game structure, and that goes into storage. And the GPUs are communicating with each other via memory and handling all this processing in memory. And then the software developer is going in and programming all of it. And that's what we get. We get magical applications. We get robots that can clean houses. We get financial algorithms that make us boatloads of money. We get medicine that changes lives. And we get armies of agents that advance materials research and create new medicines. So high performance computing is important and it has many layers. And we need to learn how to orchestrate it to create great things. But let's focus on creating great things. Let's focus on being good, being a good society, being a good planet. And I think the core here is to maintain good ethics and understand what it means to be a good life, to enjoy life, to be at peace, to create things that give us joy, and just, try to love everyone, So that's high performance computing in a nutshell. Like, subscribe, day 3 out of 30 out of the YouTube challenge.